you can have something called an interface, right, which we've already seen in the course. Right, so remember what an interface is? It's just a bunch of methods, right, with no implementation. Right, so an interface is just a specification of the methods that an implementing class must provide. Right? So specification, not implementation. Right? Usually an interface is just one or more method declarations, no method implementations. Right? Newer versions of the language let you have static methods in the interface. Right? So you're allowed to put a static method in an interface, and you're allowed to give it an implementation. There's also these things called default methods, which you are allowed to put into an interface, and you're also allowed to give a definition in the interface. Right? We're going to ignore these two for the time being and just look at the simpler case. Also remember that in Java, an interface is a type. Right? So list is an interface. Right? It's not a class. But I can store an object, right? So I can store an array list reference in a variable whose type is list. Right? So you can actually use the name of the interface as a type. Right? What can I store in T? I can store any reference to an object that implements the list interface. Right? So I can store a linked list in the reference T. Right? And I can store my list in a reference T, as long as my list implements the list interface. Okay, so any class that decides to implement an interface has to implement all the methods that are in the interface. Right? So when we implemented comparable, right, all of our classes had to have a compare to method, right? Because that's the method that's in the comparable interface. There's an important interface in Java called Iterator. So an iterator is an object that knows how to iterate over a collection of elements or a sequence of values. Right? So in other words, it's an object that encapsulates a for loop. Right? That's literally what an iterator is. If you want to loop over a list or set or a map, right, and you want to remove elements while you're looping over that collection, right, then the only safe way to do that is to use an iterator object. Right? So in other words, if you try to write a for each loop to loop over a list and remove all the elements that are, say, less than 0, that loop will probably eventually fail, and you'll get some strange exception thrown. And that's because removing stuff from a collection while you're, that's because when you remove something from a collection, it can break the iterator, right? Because the iterator doesn't necessarily know that you've modified the collection that it's looping over, right? But if you use the iterator directly to loop over the list or set, then you can ask the iterator to remove an element from the list or set, right? And now the iterator knows that it's removed an element from the list or set, and so now it can correct for the missing element as it continues to look at the rest of the elements. Right, so if you look in the list and set notebooks, they show you how to use an iterator to loop over a collection and remove stuff from the collection as you loop over it. If you write a for each loop in Java, you're actually using an iterator object. Right? You don't have to make one yourself. The language does it for you. Right? So the language actually hides the iterator object from the programmer by having the compiler write all of the necessary code for you. Right? So when you write for each string s in a list of strings, you actually end up with an iterator object somewhere. Right? So what does the iterator interface look like? It looks like this. There's a couple of methods here that you don't need to know about right now. So there's a method called hasNext, and there's a method called next. Right? So hasNext returns true if there are more elements to visit in the collection. Right? So if you have a list of, say, size 10, right? You're iterating over the list using the iterator, right? You're not at the end of the list yet, hasNext will return true. Right? When you hit the end of the list, so in other words, when you visit the last element in the list, hasNext will return false. Right? If hasNext returns true, you can call next. Right? So next returns the next element in the sequence. Right? So make an iterator, call next the first time, that gives you back the first element in the sequence. Right? Call it a second time, that gives you the second element. Call it a third time, that gives you the third element, and so on and so on and so forth. Right? If you call next and there are no elements in the sequence, you get an exception. So why is the iterator, the iterator. So that's the iterator interface. Okay. There is a closely related interface called iterable. Right? So an iterable object is any object for which you can write a for each loop. Right? So list implements the iterable interface. Right? Set implements the iterable interface. Right? Arrays do not technically implement the iterable interface, but the language pretends that they do. Right? So in other words, you can write a for each loop for an array. The compiler does something different compared to a list or set. Right? So if you can write for each blah in blah, then that blah implements the iterable interface. Right? So how does the iterable interface work? Well, it just returns an iterator. Right? And now the iterator does the work of looping over the interface. Right? So don't get these two interfaces confused. Right? So there's one called iterator, right? And then there's another one called iterable. Right? And the iterable interface is the thing that returns an iterator. Okay, so in Python, which I guess you didn't learn as your language, you can write a loop as follows. Right? So the syntax in Python tends to be more compact than Java. Right, but in Python, you can write every loop that you write looks like this. Right, looks something like this. Right, it's always for I in some object. Right, there's no for int I blah 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 blah. Right, there's no C-style counting loop in Python. Right, if you want a C-style counting loop, you have to write it like this. Right, you make a range object. Right, that range object knows how to count from 0 to 9. Right, so that's what in range 0, 10 means. Right? Starts counting at 0, goes up to but not including 10. Right? So every Python loop looks like that, which is actually really nice to write. It's a lot quicker to write. It's a lot easier to read than a C-style loop. Right? So can you do the same thing in Java? Right? Java doesn't have this nice loop. Right? The closest you can get is the following. Right? So I can write a for each loop in Java that loops over a range object. Right? So I can make my own class called range that corresponds to the Python range. Right? And a range is just, I think I tell you, oh no, I don't tell you. So, right here. No, I don't tell you, sorry. So a range object the range object that I'm going to make, it's just a counter. Right? So it can start counting at 0, it goes up to but does not include 10. Right? Can't go backwards. Always counts in increments of 1. Right? You can change it to count in increments of something else, but for our purposes, it's always going to count in increments of 1. Right? So if range implements the iterable interface, then we can write this kind of loop. Right? And you never have to write a for int I equals blah, blah, blah loop anymore. Right? Okay, so what does it look like? So I'm going to make a class called range. Right? Now range is just a counter that starts counting at some number, right, and stops counting before that number, right? So stop is the value that's 1 less than the endpoint. Sorry, stop is the value that's 1 greater than the endpoint. Right? If I want to be able to write a for each loop, the range class has to implement iterable. Right? So in other words, range has to provide an iterator object. So what do my constructors look like? The constructors should initialize start and stop. Right? I would like to be able to make a range object with this one number. So I'd like to be able to write new range 10. And that makes an object that counts from 0 up to 9. Right? So I have one constructor that just takes in the stopping value. Right? To implement it, I just chain to the second constructor, right, passing in 0 for the starting value. Right? The second constructor takes in the start value and the stop value. Right? Remember, the stop value is 1 more than the actual stop value. Right? We have a little validation check here. Right? So this range object always counts up. Right? So if stop is less than start, that's a problem. Right? So we should throw an exception. Right? Otherwise, you just set this start and this stop to equal start and stop. Okay, so because this class says it implements iterable, I need to return an iterator object somewhere, right? So I need a method called iterator right, that returns an iterator object, right? And it's an iterator whose value is an integer, right? Because I want my range to be to count using int values. Right? So you're going to return an iterator that returns a value that's an integer value, right? And now I need to provide an iterator class, right? And there is no iterator class in the standard library that's suitable for our purposes, so we have to roll our own. So I'm going to return a new RangeIterator, right? And inside the range class is the definition of the RangeIterator class. Right? So we haven't seen this before. This is all brand new. Right? So inside my range class, there's going to be another class. Right? The class is private. Right? So what does that mean? That means only range objects can use this class. Right? So only a range object can actually make a RangeIterator object. Right? No one external to the class can make a RangeIterator object. It's just a class. Right? So it looks exactly the same as any other class, right? So class RangeIterator, right? The iterator has to implement the iterator interface because it's an iterator, right? And this class here, RangeIterator, is an example of what's called a nested inner class, right? And in Java, it's normally just called an inner class. Right? So what's a nested class, right? This is a nested class, not a nested inner class, right? Inner class is something different in Java. So a nested class is a class that's defined inside of another class. Right? RangeIterator is defined inside the range class. It's a nested class. Right? Oops, sorry. Right? Now, what's the purpose of a nested class? Right? So the purpose of a nested class is you want to make a class, and its only purpose is that it's serving the class that it's in for some purpose. Right? Its only purpose is to serve the class that it's in, right? So our RangeIterator class, right, its only purpose is to serve the range class, right? And the only reason we're making a RangeIterator is so that the thing can count, right? That's all it's doing. The RangeIterator is the thing that's going to do the counting. Right? So if you implement a nested class and you realize later on that, hey, it might be useful if someone else could use this nested class, right? Then it should be a top-level class. So in other words, it should be in its own Java source code file, and it should not be in another class. Right? Now, iterators are usually defined as nested classes because it doesn't make sense to have an iterator without having its enclosing class. Right? So in other words, it doesn't make sense to have a RangeIterator if there's no range object to iterate over. Right? So in other words, a RangeIterator can't exist on its own, right? It needs a range to loop over. So this is a perfectly valid this is a perfectly good example of when to use a nested class. And it's the same is true for list-iterator. So if you look at the list class and you look at its iterator method, right? It actually returns, and you look at the source code for it, it actually returns a list-iterator. The list-iterator class is defined as a nested class of list. Okay, so that's a nested class, right? Now, I told you this is a nested inner class, right? So what's an inner class, right? So an inner class is a nested class that's not static, right? It's not static. So there's also something called a static nested class, right? So nested class is an inner class, not static. Objects of an inner class type always have a reference to an object of the enclosing class. Right? So what does that mean? If you have a RangeIterator object, inside that RangeIterator object is a reference to its range. Right? So there's a reference to the range that it's looping over. Right? An inner class object is allowed to access the fields of its enclosing class. Right? So what does that mean? It means a RangeIterator object is allowed to access the fields of its range. Right? So when I make the RangeIterator object, it's able to access start and stop. Right? Even though start and stop are private. Right? Because the class, because the because the inner class, because it's an inner class, right? It's allowed to look at or access start and stop. Okay, so what does the range iterator do? It doesn't do anything, it just counts. Right? That's all it literally does, right? So a newly created range iterator object should start counting at the starting value of its range. Right? Every time next is called, right, the iterator throws an exception if the count has reached the stopping value of its range. Right? So in other words, if the iterator reaches the value stop, it can't count any further. Right? If it hasn't reached the value stop, then it just returns the next number in the range. Right? So it returns the current count and then adds 1 to the count. Right? Every time you call hasNext, it returns true if the current count is less than the stopping value. Right? So have you reached the end of the range? No, return true. Right? Have you reached the end of the range? Yes, return false. Right? So all it's doing is counting. Right? So how do you implement the range iterator class? Right? It's a counter, so it needs a value. Right? If you look at this, this is just the counter class again. Right? So it needs a value. What does the constructor do? The constructor starts the value, right, at the starting value of the range. Right? Notice the bizarre syntax that's used in the inner class. Right? So if the inner class object needs access to the range, to the outer class field, right, you use the name of the outer class dot this dot name of the field, right? So range dot this dot start is the start value for the range object that the range iterator is looping over, right? You have to write this, right? You have to write range dot this dot start. Okay, what does hasNext do? Right? hasNext returns true if the current count is less than the stopping value. Right? The current count is val. Oh wait, the value returned by next. Yeah, so the current count is val, right? So if this val is less than the stopping value of the range, return true, right? Otherwise return false. Right? Again, notice the bizarro syntax, right? I need to access the field from the enclosing class, so I need to use the name of the enclosing class. Finally, what does next look like? Right? So next returns the next value in the iteration, right? In other words, it returns this dot val, right? So we're going to return result here, which is just this dot val, right? Next also advances the iterator 1 position, right? So it adds 1 to the current count, right? So remember what the current value is, add 1 to the value, return the old value, right? It also needs to throw an exception if there are no more values in the range. Right? So call hasNext, check if it returns not, false. Right? So if there is not a next element in the range, throw an exception. Right? The exception that you throw is no such element exception. Right? So that's specified by the next method in the iterator class. Right? And that's it. Right? So you've now got a counter. Oh, so you now, after doing all of that, right, you can now write code that looks like this. Right? So for int I in the range 0 to 10, print out I, and that gives you the values 0 through 9. Right? So in other words, you can replace any of your counting loops that count by increments of 1 up using a range object. Right? If you extend the range class a little bit, you can make it count down, or you can make it count in increments of some value not 1, right? Either up or down. Right? And the extensions are not difficult. The syntax is weird, but the extension is not difficult. All right. So at in the last class, we implemented one interface. We implemented 2 interfaces. We implemented the iterator and the iterable interface. Today, we're going to look at how to make your own interface. And then we're going to look at a data structure called a stack, which you probably have seen in, I assume you saw stacks in your okay. So we're going to implement a stack in the easiest possible way that you can do it in Java. Well, probably the second easiest possible way. And that's going to lead into implementing stacks in other different ways. How did you implement a stack in C? Did you use an array or did you use a linked structure? No one remembers. We did both. You did both? Okay, so you're going to do both again in Java. All right. Creating an interface. So if you want to make your own interface for some reason, then it looks the same as implementing your own class. But an interface is just a list of methods, so it's actually easier than making your own class. Now, you might wonder why you might want to make your own interface. And so you create your own interface when you have one or more classes that are possibly unrelated to one another, but you all want them to have a common method of some kind. Right? So here we're going to implement, you'll see an example of implementing an interface where you can print an object. Right? So objects that implement the interface have a print method where you can, that automatically prints the representation of the object to standard out. Everything in an interface is public. So interfaces are meant to describe the public interface of a class. Right? So everything in it is public. If you try to make anything inside the interface not public, the compiler will complain. Right? So either have no access modifiers in the interface, or every access modifier is public. Right? If you try to use private or protected, the compiler will not allow you to do so. So here is our interface called printable. It just represents objects that can be printed to standard output. Notice that the comment says it's not a particularly useful interface, but it's an example of a simple interface that's easy to understand. Right? So all you do is you change the word class, you change it to interface. Otherwise, things are the same. Right? You then add whatever methods you want your interface to have. Right? So in an interface, it's only the method declarations. Right? In other words, it's not the definitions. So there's no body to any of the methods. Our printable interface will have one method, right, called print. Right? It's public and it returns nothing. Right? It has no arguments. Notice that there's no body. Right? So it's just the declaration of the method followed by the semicolon. Right? No implementation. Now, you can easily modify any class that you have the source code to implement the printable interface. Right? So for example, I can take the point2 class and I can have it implement the printable interface. Right? So currently, our point2 class implements comparable. Right? Now, in Java, a class can implement as many interfaces as you want. So you just list the interfaces, separating them with commas. Right? So that declaration says point2 implements the comparable interface and the printable interface. If it implements the printable interface, it has to provide the print method. Right? So you add your print method, right? And what does it do? Well, it just uses system.out.println to print the thing, right? Which is why it's not very useful. You could do this without an interface, right? You can always print out a Java object using system.out.print. Right? But there's an example of how you could create an interface and then have a class that implements the interface. Right? And so we're going to come back to this idea, probably not this lecture, but probably in the next lecture. Right? So keep the idea of interfaces in mind. We're now going to talk about stacks. So I can go through this pretty quickly because you've all seen stacks already. Right? So these are all examples of stacks. Right? So you should know, hopefully, your data structures instructor told you that anything you do at a stack only happens at the top of the stack. Right? So you can remove the element at the top of the stack. You can add an element on top of the stack. Right? So I can put another book on top of the stack if I wanted to. Right? And so classically, stacks only support two operations. There's push, right, which adds to the top of the stack, and there's pop, which removes from the top of the stack. Classically, those are the names of the operations, but there are other names for push and pop. But classically, these are the two names. So hopefully these are the ones that you were taught as well. Right, if you try to pop an empty stack, then in Java, the appropriate thing to do is to throw an exception. Right? In C, you have to choose how you want to deal with the error condition. Right? But in Java, throw an exception if someone tries to pop an empty stack. Right? You almost certainly would have seen a picture like this before. I'm just going to quickly go through it. Right? So if I have a stack of strings and I push 5 elements onto the stack, right, your stack ends up looking like this. Right? So the top of the stack just moves up as you add elements on top of the stack. Right? When you pop, popping will remove the element from the top. So it's going to remove the E and return that back to the caller. Right? And then it'll move the top of the stack down by 1. Right? So popping a stack, it just looks like this. Right? until you get to the empty stack. So when I get to the stack of size 1, I can pop one more time, and I have an empty stack, at which point you can no longer pop the stack. Right? If you write st.pop, you should get an exception now. Okay, so where are these things used? Were you told where they were used? Or were you just told this is a stack? You were told where they're used? Okay. So the most common place that people, the thing where you would have seen it, where a stack would have been used, that you've probably actually used on your computer, is when you do undo or redo. So in any computer in most computer programs that have undo and redo, the way undo and redo works is there's some representation of a command, right? So when you do some command, like type something into your word processor, right? Some representation of that command gets pushed onto the undo stack, right? You do something else, then the next command gets pushed onto the undo stack, right? If you want to undo the previous command, you pop the undo stack, and then you undo the command that comes off, right? And then that command gets pushed onto the redo stack, right? So if you redo something, then you pop the redo stack, you redo the command, and then put it back onto the undo stack. So undo redo is typically implemented using a pair of stacks. Right? And there's lots of other applications for stacks as well. Right? In particular, they show up in a lot of algorithms, especially when you try to do things on recursive structures like trees. And there's other places as well. Did they show you how to convert a recursive method to a non-recursive method with a stack? No? Yes, no? Okay. So did they show you recursion? They did, right? Okay. So if you have a recursive method, or a function that you want to convert to the non-recursive version, one way to do it is to use a stack. Right? So there's a trick that you can play. Not a trick. There's essentially what you end up doing is you end up simulating how functions or methods work on your computer manually. And I think I'm going to show you an example of that either later today or in the next lecture. So if you want to reverse a sequence, you can use a stack, right? So don't do it this way. But you could use one. I'm going to show you the picture first, and then we'll come back to the algorithm. Right? So if I want to reverse that list T, right, then one way to do it is to use a stack. Right? So the way you do it is you take the elements of the list, and you just push them onto a stack. Right? So I push the A onto the stack, I push the B onto the stack, I push the C onto the stack. Right? You should know that a stack is a first in, last out. Right? Last in, first out. So LIFO data structure. Right? So the last thing you push onto the stack, that's the first thing that comes out. Right? So when you pop the stack, the C comes out first. Right? So if I take that C and I put that into the resulting list, right, that effectively reverses the list. Right? Now, you shouldn't do this because this particular algorithm ends up taking up, how much memory do you need for this algorithm to run? You need 2 times the size of the list. Right? I need memory for the stack. Right? And then I need memory for the resulting list. Whereas you could just reverse the list directly, right? By looping over the list backwards and putting the elements directly into the result. Right? So the method, if you wanted to use a stack, looks like this. Right? So I want to reverse a stack. I want to reverse a list T without changing T. Right? I want to return the reversed list as a new list. Right? So we make a new list. Right? If you're going to use a stack, you make a new stack, right? And you simply push every element from T onto the stack, right? So for each string S in T, push the string S onto the stack, right? And now pop the stack until it's empty, right? So while the stack is not empty, right? Pop the stack, take the element, add it to the result, right? And that gives you a reversed list. So a stack actually looks a lot like a list, right? So if you look at this picture here of that stack, right? If you sort of turn it 90 degrees to the right or 90 degrees clockwise, right? Then it looks exactly the same as that list there. So pushing an element onto the top of the stack looks exactly like adding an element to the end of a list, right? Popping an element from the top of the stack looks exactly like removing the last element from the end of the list. So in Java, one way to implement this stack is to just use a list. Right? So if I want to make a stack class, right, then internally, I can just hold the elements using a list. Right? So I'm going to use an array list in this case. right? And the field, I'm just going to call it stack, right? Elem or elements or something probably would have been better. But anyway, it's called stack, right? We need a constructor, right? What does a constructor do? It initializes the field. So our constructor simply makes an empty array list, right? Which gives us an empty stack. We've decided to add a size method so that someone can find out how many elements are on the stack, right? How many elements are on the stack? Well, it's just the number of elements in that list, right? So you just return this.stack.size. Right? Pushing an element onto the stack is equivalent to adding an element to the end of that list. Right? So to push that element onto the stack, you just add the element to the end of the list. Right? Now that's an array-based list. So adding an element to the end of an array-based list is usually has complexity big O1. Right? In a few lectures, you're going to see, though, that that's not always true. So occasionally, adding an element to the end of an array-based list has complexity big O of n. Right? And you'll see why when we actually implement a list. Pop is equivalent to removing an element from the end of the list. Right? So I want to remove the last element of that list. Right? I need the index of the last element. That's just this size minus 1. Right? Now use the remove method. That removes the element from the list and returns it back to the caller. Right? So now we return elem back to the caller, and that's it. Right? You're done your stack implementation in about 2 minutes, right? Or less. Right? It takes very little time to implement the stack if you have an existing list class. Right? This stack can grow to any size, right? Because the list, right? The internal list takes care of allocating and deallocating memory for you. Right? So if the list needs to grow, it automatically allocates a new array, copies the elements from the old array into the new array, and carries on. So it's very nice. So having this list data structure in Java is, it's really nice to have, especially if you're coming from a language like C, right, where you're taking care of all your memory management on your own. That's not the only way to implement a stack, right? So you saw that you can also use some sort of linked structure, right? So a linked list-like structure to implement a stack, right? I can use an array rather than an array list to hold the stack, right? There are other ways to implement a stack as well. Right? So there's many ways to implement a stack. They all have their own disadvantages and advantages. Right? So for example, if you use an array compared to an array list, an array uses slightly less memory than an array list, runs very, very, very slightly faster. Right? The disadvantage is, though, if you want to grow the array, you have to manually do it yourself. Right? If you use a linked structure, using a linked structure usually occupies more memory than using an array or an array-based list, right? But if you use a linked structure, you can guarantee that push is always in O1, right? Which you can't guarantee with a list or an array-based list. An array, right? Occasionally, push for an array or array-based list is in ON. Oops, sorry. Right? So there you have several possible different implementations, each with their own advantages and disadvantages, right? As someone who might be implementing a stack or someone who might be creating a library of some kind, right? You can actually provide all three implementations and let the user pick what implementation they want to use. Right? Now you want all your stacks to have the same interface, right? So you want them to be interchangeable. So someone can use an array-based list, or they can use an array list-based list, or they can use a linked list-based list. Array. Right? Someone can use an array-based stack, a list-based stack, or a linked structure-based stack. Right? And they should be able to use them interchangeably. Right? So the way you do that in Java is you define an interface for the stack, for all stacks. Right? And then you provide separate classes for the different implementations. Right? And now users can pick which implementation they want to use that's most appropriate for their purpose. Right? So the Java standard library provides you with an array-based list and a linked list. Right? You get to choose which one you want to use. Right? It provides you with many types of sets and many types of maps, right? All having their own advantages and disadvantages. Right? The user gets to pick which one they want to use, and they're all interchangeable. Right? So that's the power of using interfaces.